So today we're going to be talking about deductive reasoning. Deductive reasoning involves facts, accepted rules, properties, definitions, and logic. Okay. Yesterday's inductive reasoning was based on what you had experienced. Okay. This is going to be based on things that you know for sure. So let's say I show you this triangle. What do these lines mean? They're the same length. So what kind of a triangle is this? Isosceles. And you know that because the definition of an isosceles triangle is a triangle with two sides of equal length. So we can prove this is a triangle based on the fact that we know the definition of a triangle. That's logical reasoning. So that's deductive reasoning. Okay. If I had just seen this shape and someone had told me that shape was a circle, if I showed you that was a circle, would you agree? Yes. Relatively speaking, right here. What if I did this? Is that a circle? Yes. Is this a circle? Yes. Yes, those are circles. Are you saying they're circles because you remember the definition of a circle? No. You're telling me you know it's a circle because you know what a circle looks like in your experience. The definition of a circle is the set of all points equidistant from one point. So that point that's in the middle, all the points on the circle make up the circle because they're all the same distance from that point. What is that distance called? Radius. The radius. But that's not what you were using. However, it was what you were using when you told me that that was a triangle. So we're going to work through several forms of deductive reasoning in this lesson. Here's the logic part, the if-then. If it is raining, then we have inside recess. That's the rule at this school, right? So that's a rule. So I look outside, I see that it's raining. What do you know? We have inside recess. You know that for sure. Now let's say that you're new to this school and you don't know that we have this fancy rule to keep you dry. But you noticed that the last time it was raining, for some reason we stayed inside. And then the next time it was raining, we stayed inside again. And you say, ooh, it's raining today. I bet we're inside. That's inductive. Following the rule is deductive. And sometimes we come to the same conclusion. Okay? Yes?
I've seen on the isosceles triangle, this is called deductive reasoning. But I thought deductive reasoning is when you prove it not, like you add one counterexample to make it true.
No. Deductive reasoning is reasoning using facts, accepted rules, properties, and definitions. This is the one that we use to prove things are true. Now, sometimes we use it to prove things are not true. But both kinds of reasoning can be used to prove, or that's a lie. Both can be used to disprove. Which one can be used to prove? Deductive. Okay. If I'm watching a movie, then I eat popcorn. If I eat popcorn, then I drink Dr. Pepper. What is a conclusion you can make given all this information, Mia?
I'm watching a movie that person eats popcorn and drinks Dr. Pepper.
Yeah. And you can jump straight from watching a movie to drinking Dr. Pepper. You know that if I'm watching a movie, I am also drinking Dr. Pepper. It's a requirement. If I'm in a boat, then I'm wearing a life jacket. So you know that I'm in a boat. What do you know? I'm wearing a life jacket. What if I am not wearing a life jacket? I am not in a boat. If that happens, then this doesn't happen either. Now I'm going to ask about the converse of that statement. The converse is when you switch the hypothesis with the conclusion. So if I am wearing a life jacket, then I'm in a boat. Is that true based on what you know here? No. But you don't know it's true, do you? Because I could be on a jet ski. I could be on a tube. I could be standing on the dock because my grandpa used to make you wear a life jacket if you were standing on the dock. Yes?
Wait, what's the converse?
The converse is when you switch the hypothesis and conclusion. So if the original statement is if A, then B, the converse is going to say if B happens, then A happens. Sometimes the original statement and the converse are true. Sometimes only one of them is true, only the first one. You have to look at it. You have to test it.
I didn't know pepper, then I eat popcorn, and if I eat popcorn, I'll eat movie. That's not always true.
That's not always true.
Isn't it like the random rhombus?
It is kind of like that, yes. If it is a rhombus, then it is a square. That's not necessarily true. If it is a square, then it is a rhombus.
Like the dogs and the
That one should like the dogs and the poodles.
Oh, when you switch the converse, you switch for the hypothesis.
Conclusion. Okay. Using a Venn diagram is another form of deductive reasoning because Venn diagrams are formed using rules. So I'm going to say this box is everybody in G period math. And I'm going to say that this circle is everybody with brown hair. And I'm going to say this is everybody who likes cheese. Okay. What is this section?
With brown hair.
People who have brown hair who like cheese. What's this out here? Okay. People who don't have brown hair and don't like cheese. Okay. Can all of you figure out where you fit in this diagram? You're figuring that out using deductive reasoning. You're following the rules. You're saying, if I have brown hair, then I go in this circle. Oh, I don't have brown hair, so I know that I don't go in that circle. If I like cheese, I go in this circle. I do like cheese, but I know I don't have brown hair, so I know I'd have to be in that part of the Venn diagram. Venn diagrams can also look like this. They can actually look lots of different ways. This one I kind of call the egg because this circle is entirely within this circle. So let's keep that this is G period, and I say this is everyone who's wearing a uniform, and this is everyone who's wearing a polo. Well, because the polo circle is inside the uniform circle, that means that everyone who's wearing a polo is also wearing a uniform. Is that true?
Yes.
Yes, every one of you that has on a polo has on a uniform. Is it possible to be in this circle, but not in this circle? Yeah, everyone who has an Oxford fits in this part of the circle. Is it possible to not be wearing a uniform? For me, it is. So here I am out here in the box, but not inside the circle. All of that is deductive reasoning. If this is everybody who plays fall Hockaday sports, do I have any overlap here in these two circles? So I might say something like, this is everyone who plays field hockey, and this is everyone who plays volleyball. And then who goes here? Everybody who's in cross country. Or if you don't play sport at all, then you're not in the box at all. Right? Everybody doesn't fit in the box necessarily, but everybody who's in the box has to play a fall Hockaday sport. Okay? If I say that the box is everybody who likes sushi, well, does everybody like sushi? No. So some of you wouldn't be in the diagram at all. That's fine too. Okay? So that's another form. I like this one. We don't have to go through this, but following a flow chart is using logical reasoning. So where am I? I'm in public. Is there a leash law where I am? Yes, there's a leash law. Okay, I have to leash my dog. There's not a leash law. Well, did someone just ask me to leash him? Yes, I ran into an old lady at the park who's terrified of my dog. Yes, then I need to put him on a leash because that's the kind thing to do, right? So as you follow through this, you can figure out where you need to be based on all the rules. I can show this to you later if you want to see it later. All right, this is good. I need to move my thing over a little bit. How can use an expression to represent an even number? Let's move this over. Okay, first we need to talk about what an expression is. We know an equation is something that has an equal sign. An expression is part of an equation that doesn't have an equal sign. So I'm going to give the first example, and you guys can give me some others. 5x plus 12 would be an example of an expression. Can you give me another example?
12x plus 12.
Okay, what else?
3y plus 15.
And even just 3y. It doesn't have to have any addition or subtraction. 7 is an expression. X is an expression. All right, anything like that. It could be x divided by 4 would still be an expression. It could be 1/2 x. All right, all of those things are expressions. So we want an expression that could represent any even number. Well, if I put 4, does 4 represent any even number? It only represents the number 4. So I'm going to switch over here for a second. Let's talk about what makes an even number an even number. Shout out some even numbers.
2, 4, 2, 1,243. I mean 7. I mean 8. What?
Okay, what makes these numbers even? They're divisible by 2. And what it means when we say they're divisible by 2 is I can say each one of these is 2 times something. What's the first one?
2 times 1.
What's this one?
2 times 2.
And this one is? This one is 2 times 6. Okay. So we need an expression that represents any of these. What do you think? An even number times x. 2x is the simplest one we can use. But any even number times x would work. I always use 2x because I like to keep my numbers I'm working with small if I have the choice. If I want the number that comes after this one, how do I get from one even number to the next one? Add 2. So if I wanted another even number, I could say 2x plus 2. Or 2x plus 4. Did I say 2x plus 3? No. So all of these are representations of even numbers. What if I wanted an odd? 2x plus an odd number. For example, 2x plus 1. Because that takes an even number, right, and adds another one, it always makes it odd. Yes, but I need a way to represent an odd number before I can do that. Does that make sense? So the answer to the first one, a way to express any even number is going to be 2x. And then I would make a list. We could also use 2x plus 2. We could also use 2x plus 4, and so on. And then you said for an odd number, we could use 2x plus 1, or 2x plus 3, or 2x plus 5, so on. All right? How can we prove that all these expressions up here on the first list are even? That would be inductive reasoning, right? If we just plugged in numbers, you know. What do we know about even numbers? They do. What definition did we give for even numbers? They're all divisible by 2. So let's take one of these expressions. Let's take this one. Is 2x plus 4 divisible by 2? What do I get when I divide it by 2? X plus 2. This is even.
But x plus 2 is not.
Right. But I proved Because X doesn't have to be even.